So hello everyone, my name is Raúl Garcia. I work at Mein Auto as Team Lead CloudOps. I was before at DKIX. I don't know if you have been last year here also for my talk. Last year I was talking about Kyverno policy implementation and how you can harden your Kubernetes cluster with it. This year I want to talk about the journey at DKIX and also DENIC to a default deny Kubernetes network policy implementation within the Kubernetes clusters of these companies. And yeah, I'm also the organizer of the Cloud Native Frankfurt meetup group. So should you be from close by Frankfurt, feel free to show up on one of our next meetups. We will inform on the Cloud Native Frankfurt meetup page. We are on LinkedIn. We are also, you can also find us on the website of the Cloud Native Computing Foundation. And yeah, we are always happy to see new faces. And if you want to give a talk there, also feel free to let me know. All right. First question, who of you is already using an implicit deny all policy within their Kubernetes cluster? Okay, yeah, this is actually what I was already expecting. And it's quite surprising actually, because if you think about like the past, when applications were running in virtual machines, people were always trying to segmentate networks. So you always were having like a network for the front-end applications, then you were having a network for back-end application, for databases, and so back and so forth. So everything was segmented. This, however, has changed since applications are running in Kubernetes. A lot of companies are running front-end applications, back-end applications, databases, and a lot of other applications that should not communicate with each other in the same Kubernetes cluster. So there is always happening a lot of hardening when it comes to capabilities or do not run as root user and so on, but network policies are quite often forgotten. So just a reminder to that, why deny all matters. So first of all, in Kubernetes, the default behavior is an allow all. So pods can always communicate freely with each other. There is no limitation as long as there is no network policy in place. Then it is quite often also the fact that application owners, not only from dev teams, but also from platform teams, don't know exactly how their applications are communicating with each other. What flows are existing, what is my application connecting to, or where are connections coming from to my application. This is also behavior that I've seen also quite often, and I'm pretty sure that if you ask within your company, also the majority of people is not really sure what connections are being built. And last but not least, something that we, especially in the Kubernetes world, lack quite a lot is visibility. So are you aware what connections are being built by your container or your application, or are you not? And I have the feeling, or I've seen so far, that most of the times you are not aware. And there has been solutions provided, like for instance in Cilium Hubble, or also now Calico has also provided Calico Whisker, but still these solutions, they are not very adopted nowadays, and especially also when you run your cluster as a managed cluster, for instance, AKS, you cannot enable Hubble. At Google, it is also not enabled by default, so you have to become active by yourself in order like to get this visibility. So let's do just a quick recap for the people that are not very familiar with the Kubernetes network policies. So first of all, Kubernetes policies are namespaced resources, and they work by label. So it's not like in the former times where you were saying, okay, I have one IP address and one port. Instead, in the Kubernetes world, you work with label. So your application has a label, let's say, for instance, app web server. So you would create a network policy and assign it to this pod using the label. And then you would define ingress and egress rules also using labels. So compared to what you maybe are also using as a terminology like incoming, outgoing traffic or ingoing, outgoing, in the Kubernetes world, we use the terms ingress and egress for these definitions. And again, just to make it even more aware of it, in the Kubernetes world, the default behavior is allow all, as long as you do not define anything else. But there is also a limitation when it comes to the usage of Kubernetes network policies. You cannot define deny rules. You can only define allow rules. So this is also something that makes it complicated when you want to make this journey to default deny. And last but not least, you cannot define any policy tiers, but I will show you a quick example of how these network policies are exactly working. So let me, yeah, good, this works. So here we have a graphic showing what basically the transition within Kubernetes can look like. So in the beginning, when you run Kubernetes without any network policies, you have this situation. So this square is the pod. On the left side, you see ingress traffic. On the right side, you see egress traffic. No network policies means default allow, so all pods can communicate with each other. So all these three pods could easily talk to each other, ingress, egress, whatever you want to do. Once you define a network policy for a pod and assign it using the label, this changes directly. And it changed in a way that this default allow changes to a default deny for the selected pod. So it means everything not defined within the network policy is from this moment on denied. So if we look then here on the right side, here we can see we have two pods, and on the one side we can see a black one. Let's say this is still blocked traffic, and the white one, the traffic that is allowed to pass. Whoops, this was the wrong button. So we can see that, for instance, now it could have been that someone has defined that the pod up here is allowed to do an egress connection to the pod down here. And the pod down here is allowed to get an ingress connection from the pod up here. So it means in the Kubernetes world, you define ingress and egress. You define who is allowed to talk to me, and you define who am I allowed to talk to. All right. That's about the recap for network policies. So next, let's talk why Calico. I mean, I know Cilium is the cool kid on the market. Everybody's basically talking always about Cilium. However, in the company that I've joined, or at Dikix and Dinig at these times, we were already running Calico on the clusters before we started to think about, okay, hey, we want to implement network policies. So due to the fact that it was only network policies that should be enabled, we said, okay, it does make any sense to switch the CNI now. So we stayed with Calico, we were fine, everything was working good, and we got exactly what we needed already also from this CNI. And I mean, as we look nowadays, Calico Whisker has been also released, so this is also now something that could bring in some more capabilities to even stay with Calico. So what else did we use from Calico? So definitely the global network policies, because we wanted to deploy a policy that covers the whole connections within the entire cluster. Not namespace-like, but say for the entire cluster, we want to deny traffic or we want to allow traffic for all pods that are located in the cluster. I will show you also some examples in the coming slides. Then what we also got from Calico is we got the possibility to define an explicit deny rule. This was important for us for the transition phase because we don't want to deny the entire traffic from the beginning, but we wanted to deny section-wise so that people can work step by step to this deny all. Next, Calico also allows you tiered policy model. So you can define base policies, team policies, and then you can enable logging. It's a bit cryptical when you enable logging because you get a lot of information in this log line. So you have to basically extract what exactly you want to see from the log line. But you can enable it, and it's pretty easy to use once you have it enabled. And like I said, yeah, we were already running Calico, so that's why we stayed with it. Let's talk about the transition phase. So how did we get from these clusters to the default deny? And I can tell you there were already running a lot of applications And all of them were already in production. And of course, we wanted to make the teams make this transition without any service interruption. So we tried to figure out the smoothest possible path for us and also for them. So when we started with this whole implementation or this whole transition, we first of all started to think within the platform team, what are connections that the cluster or the pods from the teams are doing, but they do not, it's nothing that they manage by themselves. So let's say, for instance, a connection to the DNS server. They need to resolve addresses. So this is something we should cover already for them. Connections, for instance, also coming from the Prometheus server in order to scrape metrics. This is also something that we covered, because why should they cover them? They do not know where the Prometheus is running, in what namespace. It is more or less a platform service. So we tried to cover as much as this, let's say, platform-related services for them, so that they can really focus on what their application needs to be allowed to. Next to this, we also enabled we also defined two common path policies. One of them is the internet access allowed, and the other one is the API server access allowed policy. Why did we do this? I mean, when you have no policy in place, basically every container running in your Kubernetes cluster is allowed to initiate a connection to the internet. Why should they be able to do that? Most of the pods don't need to spin up a connection to the internet. So we blocked this as long as there is no pod having this label in place. So only pods that had the internet access label allowed were able to initiate a connection to the internet. Next topic is also the same with the Kube API server. Why should a pod talk to the Kube API server if it is not an operator or, for instance, a GitLab runner? There is no real reason. So the connection can also be blocked. Once we had this in place, these allow policies, we deployed our deny policy so that everything that is not covering these labels was blocked. Once we had this in place then, we knew that all connections to the internet and to the Kube API server were handled. So we went over and created an implicit deny policy that was logging everything, but then allowing it, so that we do not create any service interruption for the teams. And then once we had achieved this, we deployed the enforce deny all policy. So let's have a look how this all looks. So this is basically a small outset of the small section of the code of the predefined allow rules. Okay. So what we have here is the internet access allow rule, for instance, where we say that everybody having this label, every pod having this label in place, is allowed to communicate to networks which are not part of these CIDRs. So this is private CIDRs, means that all public CIDRs are part of this one, of this rule, so they can communicate to the internet. Next, we have implemented the rule that says ingress allow for the Prometheus instance, which is located in the monitoring namespace and comes with the Prometheus label, means that this instance can do ingress traffic to all pods running in the cluster. And then we also defined egress rules so that every pod in the cluster can also do DNS requests against the Kube DNS that is running in the cluster, because also this is necessary. If you block this, DNS resolution for the pods is not working anymore. So this is basically like a set of policies that we predefined and that which we gave an order lower than the Kubernetes network policy order itself, because the Kubernetes network policies always have the order 1000. So means this one could also not be overwritten by any team or any member of any team which was, for instance, doing any mistakes on creating his policies, and by that, for instance, overruling what we have defined here. Okay? So once we had these policies in place, which were then basically allowing these standard services, we moved over to our phase one, which we called deny internet and Kube API server access. So in this phase, the only important thing for us was that we block access to the internet for unlabeled pods and access to the Kube API server for unlabeled pods. Means what we were still allowing ingress from everywhere, and we were also still allowing communications, egress, to all private siders. But what was not allowed anymore was connection to the Kube API server sider and connections to the internet. Once we had this in place, we were seeing in our logging solution that there was coming up a lot of log lines showing connections from containers that were trying to build a connection to the internet or to the Kube API server. This was still not the same amount of logs that we were seeing when we moved on to the next phase, but still, this was some kind of like disturbing because you were seeing like a huge amount of logs. Good thing is, in this approach, we went with the deny all at the end, which we could say was creating a service interruption. But since all teams knew that they are not relying on these internet services, that this was mostly like, for instance, uploading a file or uploading or pulling some kind of information from the internet, we could say, okay, it's fine not to do a denial. If you definitely know that you rely on some kind of like internet connections, then of course you should, instead of having a deny here, set an allow so that these connections still are passing. But why did this happen the way it happened? Because you have to imagine that this one runs first. If this is covering what you're trying to do, then the evaluation of policy stops here. If it does not cover what you're trying to do, it goes down to this one. If this one covers what you're trying to do, it stops here. Otherwise, it moves on. Then the Kubernetes network policy comes, which is order 1000. If this covers what you're trying to achieve, it stops there. If it doesn't cover what you're trying to achieve, it comes to this policy, the very last one. And then it happens, what defined is here is going to happen. So if it is allowed, good, then and, otherwise it logs and denies. So this is basically how the order works when you use network policies in Kubernetes. So once we then had figured out how things are behaving and that people, and there were no log lines anymore because people had finally written all the policies or had used the labels that we had provided in order to allow the pods to communicate to the internet or the Kube API server, we enabled this policy. This policy was then removing the deny that we had in place before, but for us it was at this moment important to see what private networks was being blocked now, or what connections would have been blocked now within private networks. And since this was more or less also the end state for our phase 3 policy, we just wanted to also to make it as lightweight as possible. That's why we went over to this solution in this state. So here, basically, we were logging every private connection that did not have a Kubernetes policy in place already. And same also every egress connection that was also not covered by any policy from before. Once this phase was done and we were not seeing any logs anymore, we could say that all connection flows that were occurring in the cluster are covered now. So what we did then is we changed the allow to deny in the last action. We were still logging, of course, because we still need to see when a connection is being dropped by this policy. And we not only were logging, we also created alerts once we reached this level, because the people were not that actively looking into the logging anymore, since they thought, oh, well, I've covered all the network policies that were missing. But we then created alerts that were every time that a new log line was appearing, raised an alert so that people actively look into it again. Because otherwise you will drop connections, nobody gets notification out of it, and then you will somehow start to troubleshoot and nobody knows where the issue comes from. So once you reach this point, it is very important that you have some kind of alerting for the dropped connections. But at this point, you can say for sure that all connections in your cluster, or they are defined, or they are blocked. So, happy guy. This was basically the information security guy. So, what are the lessons learned? First of all, you can't protect from what you can't see. So if you have no monitoring in place or no logging in place in order like to see what connections exactly are flowing in your cluster, you have no idea, and then it's hard to figure out if you are safe or not in that moment. Next, you have to give the teams like the possibility to understand what you are logging there. Because if you look into the log lines that Calico is producing on the nodes, they are quite cryptical. There are a lot of information in these lines that's quite hard to figure out what it is saying. So you should extract as good as possible what is really the source IP, the source port, what is the destination IP, the destination port, and if you can somehow enrich it, then with the name of the pod and the namespace that it is correlating with, then you have really a very good visibility for the teams. Otherwise, it is also good like to just provide them with, I don't know, an alias where they can search for this IP address and directly find the related pod for it in the cluster. Then definitely let teams opt in to like these common patterns of communication. Because like if you would tell them, you want to communicate with the internet, figure it out by yourself how to implement this rule. That's going to be a hard time. Same also like for topics like DNS, monitoring and so on. Give them, like handle all these critical passes for them and make it as easy for them as possible to really get into the network policy topic. And then last but not least, definitely expect workarounds. I mean, you won't believe it, but people will get creative and they will figure out ways how to bypass your default deny all. I mean, who knows what this policy is doing? Exactly. So this policy is basically this user trying to flex policy. It's allowing for the pod with the label app I hate network policies, all egress and all ingress connections. I mean, this is like a namespace policy, so it's clear that this is only working in this namespace for this pod, but still, this is basically like breaking what we have defined with this global network policy. So what could you do in order like to not have people do this? You could write, for instance, validation policies with Kyverno. But I can tell you, because I did write one, it gets very long. Because you have to handle so many situations. They could also write down, for instance, CIDRs there, like opening like a huge CIDR instead of like using Kubernetes labels, because of course you can also add IP addresses as endpoints. And there are so many possibilities they could use it, like to just work around your network policies. So don't forget that people, they will create you headache when you don't work out on such possible workarounds also. And then, from my assumption, if you do so, the result will be definitely that you will block all unknown traffic that is occurring in your Kubernetes cluster. And trust me, there is more unknown traffic occurring than you would expect it is, especially like pods sending some third-party applications sending out telemetry data. Then also known flows will be preserved because you have been seeing them before blocking them, and hopefully no service interruption. All right, that's it from my side. Thank you all for attending, and should you have any questions, I will be available now, and I think we still have 5 minutes or a bit more. So.